Now say from example 1 that although we did not know the source driving a voltage, potential, and current through a resistor, by connecting an open circuit voltage source, V sub OC, in series with the Thevenin resistance, R sub T, such that we could connect the source to our resistor R from our previous example and determine our voltage, potential across and our current running through it. We denote this as a Thevenin equivalent circuit, where the Thevenin equivalent is driven by an open circuit voltage source connected in series with a Thevenin resistance. Now if we apply KVL around our circuit, we would have minus VOC plus our voltage potential across our Thevenin resistance, which would be I, our current running through it, times our Thevenin resistance, plus V, our voltage potential across our load resistance. Or, solving for V, V would be equal to minus R sub T, our Thevenin resistance, times our current I, plus our open circuit voltage. And we see this expression is equivalent to what we derived from our previous example. Now consider the situation where we want to drive our current I through our load resistance R sub L to establish a voltage potential V using a current source. To do such, we will have our current source I sub SC connected in parallel to our Thevenin resistance, R sub T. And this non-ideal source is connected to our load resistance at terminals A and B. This particular configuration is denoted as a Norton equivalent circuit. Now, to determine our voltage potential across our load resistance, we'll apply KCL at node A, where we have I sub SC entering, and we'd have I going through our load resistance, as well as our voltage potential V per our Thevenin resistor, V sub T exiting node A. Now, expressing in terms of V, our voltage potential across the load resistance would be equal to the negative of our Thevenin resistance times our current I, plus our Thevenin resistance times our short circuit current. Now if we recall, our Thevenin resistance was equal to our open circuit voltage per our short circuit current, and make this substitution for the last term in our previous expression, our voltage potential across our load resistance would be equal to negative of our Thevenin resistance times I plus our open circuit voltage, which is identically equivalent to the expression we've created for our Thevenin equivalent circuit. That is to say, we have source equivalency between our Thevenin and Norton circuits. That is, if we have a voltage source connected in series to a resistor, this would be equivalent to a current source connected in parallel to a resistor, if and only if we make the following proper conversions. When converting from a current source and a resistor in a parallel configuration to a voltage source and a resistor in a series configuration, we have the following. We apply Ohm's law, such that our source voltage would be equal to our current source I sub P times our resistor R sub P, where our resistor R sub S has to take the same value of R sub P. That is, when we go from a Norton equivalent to a Thevenin equivalent, we determine our source voltage, i.e. our open circuit voltage source, by multiplying our short circuit current times our Thevenin resistance. Now, when we go from a Thevenin equivalent to a Norton equivalent, that is, as we go from Vs and Rs to Ip and Rp, we'd have the following. We would use Ohm's law from our previous equation, such that I sub P would be equal to V sub S per R sub P, or our short circuit current would be equal to our open circuit voltage per our Thevenin resistance, where our series and parallel resistors R sub S and R sub P would have the same value, i.e. be equal to our Thevenin resistance.